You ever stop and think about what it really takes to teach a machine to, well, think? Not just to be some perfect copycat, but to actually understand? It's like one of the biggest puzzles in all of AI. And it all comes down to this really delicate balancing act. Let's dig into how we solve it.
So here's the big question we're tackling today, right? How do we get a machine to actually learn something, not just memorize it? I mean, how do we build a model that can take what it knows and apply it to brand new situations it's never seen before? That, right there, is the absolute core challenge of machine learning.
Okay, so to really get our heads around this, let's think of a machine learning model as a student. It's a pretty good analogy. First up, we've got to understand what this student is even capable of learning on its own, just by looking at the books we give it.
And that's where model parameters come in. You can think of these as all the little facts and formulas the student crams into its brain straight from the textbook. This is the core knowledge it learns directly from the data. For a simple line on a graph, it's just the slope and the intercept. But for a massive neural network, we're talking about millions, even billions of tiny little weights. The key thing here is that the model figures all this stuff out for itself during training.
But, and this is a big but, the model doesn't just learn in a vacuum. Nope. Before the studying even kicks off, we, the data scientists, we have to set the rules of the game. It's like we're giving the student a study strategy before they even crack open a book.
And these are the hyperparameters. See, these aren't learned from the data at all. These are the control dials we're turning beforehand. Things like the learning rate, which is basically how fast the student crams, or the number of layers in a network, which is kind of like how complex we decide to make the student's brain. So we set the study plan, and then the model gets to work doing the actual study.
And this slide just lays out the difference perfectly. On one side, you've got the model parameters. That's the stuff the model learns from the data. It's all internal. And on the other side, the hyperparameters. Those are the rules we set before training even starts. They're external. You really can't get one without the other. You can't get those learned parameters until you've set the rules for how to learn them. They're totally different, but they absolutely need each other.
Okay, so what happens if we give our student a less than perfect study plan? What if it gets too good at just studying the textbook? This is where we hit the main conflict of our whole story, the real danger of a model that learns too well.
And this quote really just nails it. An overfitted model is a mathematical model that contains more parameters than can be justified by the data. It basically means the model has become way too complex for the problem it's trying to solve. It's kind of like using a sledgehammer to crack a nut. Sure, you'll get that one nut open, but you'll make a huge mess, and you definitely can't do it again reliably.
So let's bring it back to our student. Overfitting is like that student who doesn't actually learn the concepts for the big test. Instead, they just memorize the exact answers to every single question in the practice book. Of course, they're going to ace the practice test, but the second they see a slightly different question on the real final exam, they're completely lost. Why? Because they learned all the random noise, not the actual signal.
And this chart, this shows you the classic telltale sign. Just look at that training error. It's going down, down, down. The model is absolutely crushing the practice questions. But look at what's happening to the validation error at the same time. That's its performance on new stuff it hasn't seen. It starts to climb back up. That growing gap between the two, that is the giant red flag for overfit.
So how do we fix this? How do we stop our model from becoming a professional memorizer and actually check for genuine understanding? Well, we do it pretty much the same way any good teacher would, by giving it a whole series of different tests. What we do is we split all of our data into 3 separate piles. First, you've got the training set. That's the textbook. It's the biggest chunk of the data, and it's what the model studies to learn all the patterns. Then there's the validation set. Think of this like a bunch of practice exams or quizzes. We use this to tune our hyperparameters, to tweak that study strategy, and keep an eye out for overfitting as we go. And finally, we have the test set. This is the final exam. It is kept under lock and key, totally separate, until the very, very end.
And look, the difference between the validation set and the test set is absolutely critical. The validation set is part of this whole feedback loop, right? We test the model, we see how it did, we go back and tweak our study strategy. But the test set, that is a one-shot deal. You use it once. Using it more than that would be like letting a student take the final exam over and over and over until they finally pass. It doesn't give you a real grade. It gives you a fake, totally biased result. It doesn't tell you what the model actually knows.
Now, this might all sound a bit abstract, a bit academic, but I promise you it's not. Getting this balance wrong, the balance between learning and just memorizing, it has massive real-world consequences. We're talking about things that affect our daily lives.
Take a hospital, for instance. Imagine a diagnostic model that overfits to its training data. Maybe it just memorizes the specific quirks of patients from one single hospital. Well, the moment it sees a new patient from a totally different background, it could completely miss a critical diagnosis. The results could be tragic.
Or think about your wallet. A credit scoring model that was only trained on data from a booming economy might learn a very simple, very wrong rule. Giving out loans is always a great idea. The second the economy takes a downturn, that overfitted model is going to fail spectacularly, putting both banks and regular people like you and me at huge risk.
And on our roads, the stakes just couldn't be any higher. If a self-driving car's AI has only memorized what pedestrians and other cars look like on perfect sunny days, that car becomes a massive safety hazard the very first time it drives into fog or rain or snow. Generalization isn't just a nice-to-have feature here. It is an absolute necessity.
So all of these high-stakes situations point back to the very same fundamental challenge. And to avoid these kinds of failures, we really need to burn 3 core principles into our minds whenever we're building one of these models.
Okay, first, always balance your model's complexity with how much data you actually have. Don't bring a sledgehammer to attack. Second, protect the integrity of your test set at all costs. Never, ever, ever teach to the test by using it for tuning. And third, always be on the lookout for that gap between training and validation performance. It is your best early warning system that something is going wrong.
Which leaves us with this one really crucial question for the future. As we hand over more and more important decisions to AI, how do we make absolutely sure that what we're building is truly intelligent, and not just an incredibly sophisticated mimic? Honestly, the answer to that question is going to define just how much we can trust the machines we create.